this video, we're going to talk about the different properties of waves and use them to solve problems. So we've got a wave that looks like this. If you remember from our first video on reflection, this is a sinusoidal wave, or also called a transverse wave or periodic wave. The highest point on the wave is called the crest, and the lowest point on the wave there is called a trough. The distance between the center line and the crest, or the center line and the trough, is called the amplitude. Remember that the amplitude is not the distance from the crest to trough, it's just center to crest or center to trough. And then we've got the wavelength, which is the distance from crest to crest or trough to trough, or any two equal points on the wave, and we represent that by the Greek letter lambda. Now, the amount of time it takes to complete one full cycle is called the period, and we use the variable t to represent that. If we look at the wave as a function of time and look at that on a graph like this, then the period visually is kind of the length between any two equal points on the graph. So we've got our period, the amount of time per cycle, but if we want the amount of cycles per second, then that's the frequency, denoted by f. Frequency is equal to 1 over the period and vice versa, so frequency and period are inversely related. Now let's look at these properties in more depth. So we said the amplitude is the distance from the midline to the crest. This number is always going to be positive, and again, it's not the distance from trough to crest, it's just midline to crest. The period is the amount of time it takes to complete one cycle, so again, if the wave is graphed as a function of time, then the period is the length kind of between any two equal points. The frequency is the number of cycles completed in 1 second, and it's the inverse of the period, so since our unit of measurement for the period is the second, we can say that the unit for frequency is inverse seconds. But a more common unit is the hertz, where, for example, if the wave completed 10 cycles per second, then it has a frequency of 10 hertz. The wavelength is the distance from crest to crest or trough to trough, or any two equal points on the wave. We can represent it with the Greek letter lambda, and it is a unit of length. So now let's talk about wave velocity. You might remember from chemistry class that for an electromagnetic wave, there's an equation c equals wavelength times frequency, where c is the speed of light or the velocity of the wave. This comes for the equation for wave velocity, which says that the velocity v is lambda times f. And since the period is the inverse of the frequency, we can also write this as v equals lambda over t. So now that we have all of our tools, we can do some practice problems. So in this first problem, we've got a wave where the wavelength is 8 meters, and it's traveling at a velocity of 2 meters per second. When the time is 0, the rope has a vertical displacement of positive a, our amplitude. At what time will the vertical displacement of the same point on the rope be negative a? So this problem is asking us for time. It gave us that v equals 2 and lambda equals 8, and we know from our equation of wave velocity that v equals lambda over t, which we can rewrite as t equals lambda over v. And then we plug in those values and we get that t, the period of this wave, is 4 seconds long. But the point that we're looking for is the point at which the vertical displacement is negative a. So by looking at our graph, we can see that that's going to be halfway through one period. So our answer is going to be 1/2 of t, which is 2 seconds. So our answer is C. Let's try another problem. Here, a bat chirps at a frequency of 40 kilohertz, and the wavelength of the chirp is 8.75 millimeters. The sound wave hits a tree and bounces back, giving the bat an echo 0.4 seconds later. This means that the wave took 0.2 seconds to travel to the tree and 0.2 seconds to travel back to the bat. How far is the bat from the tree? This problem gives us that the frequency is 40 kilohertz and the wavelength is 8.75 millimeters. You don't need to convert these measurements to the base unit, but I just decided to, so we've got 40,000 hertz and 0.00875 meters. And like we said earlier, the wave takes 0.2 seconds to travel to the tree. So we're looking for a distance here, but first let's find the wave velocity. Using our formula, we get that that is 350 meters per second. Now I'm going to use the velocity equals distance over time formula and rewrite it as distance equals velocity times time. And now we can plug in those values for velocity and time and get that the distance between the bat and the tree is 70 meters. Here are a few more problems that you can practice with if you like, and I hope you found this video helpful.